In this example, we want to find the transfer function, which is defined as x of s over f of s for the translational mechanical system shown below. So notice we have some fixed point, we'll just call it a wall, on the left side of our figure. And then on the right, we have a mass, which is connected to that wall via a spring with spring constant K, and a viscous damper with viscous damping coefficient F sub V. We then have a force, which is pulling the mass to the right, and our displacement is defined as positive to the right. And so what we want to do here is we want to find this transfer function where we can see our displacement, x, is our output, where our force, F, is our input. So our first step, remember, is going to be to apply our physical laws. And so a good place to start with this is to draw a free body diagram. And so in a couple videos, we're going to develop some generalized equations. So for some of you double-E's who maybe are not as comfortable with free body diagrams or similar techniques, like I know I'm not as comfortable as circuit analysis, then you can just stick to the general equations. But for some mechanicals who are a little more well-versed in some of these techniques, obviously feel free to use those. So we have our displacement x of t defined to the right as such. And in our free body diagram, we want to draw all of the forces and their directions that are acting on this mass. So of course we have a force that's moving the mass or wanting to move the mass to the right, F of t. And now we want to relate the forces that are acting on the mass from the spring, our viscous damper, and of course the mass itself. And so again, if you're a little rusty on what these equations look like, as I am, you can go to table 2.4 in the textbook, which I mentioned in the previous video. And we can see that the force on the mass due to our spring is going to be equal to the spring constant K times the displacement of the mass x of t. From that table as well, we can see that the force from our viscous damper is the viscous damping coefficient F sub v times the derivative of the displacement, or the velocity of the mass, so dx dt. And then finally, the force from the mass itself, so the mass is not going to want to move if it's initially not in motion, of course, so that's going to be m times the second derivative, or the acceleration of x of t, so dx dt squared. Okay, so those are all of the forces that are acting on our mass. So now if we apply Newton's laws, we know that the sum of these forces should be equal to 0. So we can write that as m second derivative of x with respect to t twice plus fv dx dt plus kx, so all of those are acting to pull the mass towards the left, are all of those summed to equal to f of t, which is acting to pull the mass towards the right. So what we can do then is, remember, we're looking for the transfer function as a function of s. So we want to get this into the frequency domain. And of course, we can do that by taking the Laplace transform. So taking our Laplace transform, and in order to do so, we're going to have to use a couple properties. We're going to use our linearity property because we have multiple terms. We're also going to use our differentiation property because, of course, we have a couple derivatives here. And when we're doing our derivative properties, using our derivative property in order to make it a little easier, what we're going to assume for now is that we have 0 initial conditions. And you can go back and look at our table for our Laplace transforms and see how that simplifies our work. It basically means we're not having to deal with as many terms. So if we do that, we get something that looks very similar to what we saw with our electrical network. So we get m, and then a second derivative corresponds to s squared. And now our x becomes a capital X of s plus our f sub v. Our first derivative becomes s. And then our little x in time becomes our big X in frequency. And then finally, for our spring term, we just have capital K, our constant is along for the ride, and capital X as a function of S. And then our force becomes capital F as a function of S. So now, of course, if we're looking for our transfer function that we said was x divided by f, all we have to do is factor out these terms on the left because we just have x there, so we can say our transfer function g of s is equal to x of s divided by f of s. And so if we factored out each of these terms over here, we see we have an ms squared, fvs, and a k. So what we get for our transfer function then is just 1 divided by that quantity. So 1 divided by ms squared plus fv times s plus spring constant k. So that would be how we could find that transfer function there. Now, as I mentioned, we're going to come back and generalize our equations a little bit, but before we do that, we're going to see that by using the idea of impedances for these 3 passive components, our spring, our viscous damper, and our mass, we're going to be able to make this process a lot simpler, because instead of drawing our free body diagram and writing our equation in time, we can come directly from our diagram in the frequency domain to our equation in frequency. And so we'll see that in the next video, and then we'll present some generalized equations and work one more example.